we got this one and one more. That's it for this chapter. So, we're starting today with titrations of polyprotic acids. No math, just want to show you the titration graph and talk a little bit about indicators. You guys met phenolphthalein, and that's the big one, but there's a lot to choose from. Today's lesson doesn't match at all, and after we're done talking about titration, we're going to talk about solids breaking down in water. Those have nothing to do with each other whatsoever, but they're easy. Like always, we go through the intro, we go through the long math, and then we go through the oh yeah, by the way. Today is the oh yeah, by the way. So for a titration of polyprotic acid, if you looked at the link at the end of yesterday, the one with it was the ChemGuide UK link, you probably saw, if you made it to the bottom, what a titration graph for a polyprotic acid looks like. Remember, polyprotic acids have multiple protons to donate. So all this means is you're going to get multiple equivalence points. You're going to get multiple rapid rise portions in your graph. That's it. If you remember, it's way easier to lose the first proton than the second. So it's possible to titrate to the point where you've lost the first and not the second. So you'll see a wiggle, a rip, rip, like a roller coaster, for lack of a better term, as each proton is donated. Each one has its own Ka, so each one will have its own pKa. The end. Do you need to do this calculation? No. I'm sort of glad you're looking at a computer to see the graph of the bottom chart with the acid-base indicator so you can see the difference in colors. We were doing strong acid, strong base titrations, which are pretty standard for an intro titration, and phenolphthalein is beautiful. It changes at pH of 8, it hits on the rapid rise portion right at the equivalence point. If you catch that light pink, just as it's starting, you're approaching a pH of 8, so you're within a fraction of a drop of the equivalence point when you get that pink. Perfect. But what if I'm doing a titration where my equivalence point is like 4, or my equivalence point is like 9? I can't really use phenolphthalein. If I'm going for 9, it'll be pink and past pink long before I get to the equivalence point. And if I'm going for 4, I'm never even going to get to phenolphthalein pink. So there's a variety of indicators. Do you need to memorize those? No, but I'd know that there is a world beyond phenolphthalein. So there you go. Strong acid, strong base, that is a good question. Phenolphthalein is always I feel like if I gave a lab final, I would definitely put that on there. Like, what did we use? You have to pick phenolphthalein, because there's like methylene blue, there's all kinds of good ones. On to the next already, solubility equilibria. Naha, we're back to the equilibrium eras. You know that some solids break down totally in water. Fair. You know that some solids break down a little bit. When we did solubility, I was like, oh, that says slightly soluble. Don't worry about slightly soluble. Just say yes. Just say yes. Or insoluble. Just say no. You even get a little bit of breakdown in an insoluble substance, but like just barely. Sort of the rebel molecules that won out. So, what we've got here is a way to identify how much will break down based on another K value. We did Kc, we did Kp, Ka, Kw, Kb. Now we've got KSP, solubility product. Same thing. In a saturated solution, it's full. All the participants that can be held are. So what we're looking at with KSP is a value of how much will dissolve. Okay, cool. And this will let you classify something as soluble, slightly soluble, or insoluble. We're not going to focus on that, and what's crazy about that is you'll see people defining soluble, slightly soluble, and insoluble with different values. There are different boundaries used. I'm not sure if it's by discipline, like if you're a physical chemist versus an organic chemist, or just by preference, but there's a yay and a nay and kind of this bleh in between. So we're not going to be classifying, but we will be calculating. So we're going to talk about how soluble this is. Got you an example in your packet with Na and NO3. That's a strong electrolyte. But it's a nice example because you see that solid sodium nitrate, S for solid, will break down into aqueous ions. And when you write your K value, what's awesome is this is a heterogeneous equilibrium, meaning I have two different phases, and we just ignore the solid. Solid gone. Remember, even if it's dissolving, we can say, concentration won't change that much, so just ignore the solid. Like we hate water, solid gone. So my equilibrium, no, my solubility product equilibrium, no one calls it that, it's just KSP. KSP is going to be Na in brackets, NO3 in brackets. Those are aqueous, and those are what we care about. Solubility is going to be your quantity that's able to dissolve. Check this term out. Molar solubility comes up in the problems. And it's kind of, the first time I looked at it, I was like, what is that? Molar solubility is how much of one of the ions you get in moles per liter. So it's a molarity. Just keep your eye on that. It's in moles per liter. You'll sometimes see it written out instead of as molarity in moles per liter. It's capital M to me. But be careful with this. And this is why I have this written up here. We're going to look at it with calcium fluoride in a minute. But before I do that, check out those solubilities. You're able to compare how soluble something is. And I told you, we're not going to classify it. Those are all pretty dinky. 10 to the negative 10, 10 to the negative 17th, 10 to the negative 13th. Your highest value is your most soluble. And like it says, AgCl is your highest, but it's still really crappy at 10 to the negative 10th, I think. Remember, compounds with silver aren't soluble. Yeah, there you go. So let's look at this. If I'm talking about a solubility equilibrium for AX2, it's a solid, but I'm telling you, it's going to break down. Okay, cool. Well, since it's X2, we'll say that that's a halogen. X is usually a halogen. So what I'm going to say is, I bet, and I mean, obviously, if it's like magnesium, you're going to know, it's a 2 plus charge. When I write this equation, I have to remember that there's 2 of X, so it's going to be 2X minus. Awesome. From here, I get my solubility expression, KSP, my concentration of A2 plus, my concentration of X minus, and I have to remember to square X minus because there are 2 of them. Write in K again. Here's the one tricky thing. If I tell you, and these are completely made up numbers because they would be like 1 point something times 10 to the negative something, if I tell you that A has a molar solubility of 2, 2 grams per, 2 moles per liter, I think that's an awful lot. 2 moles per liter. What you need to remember for your concentration of X is to multiply it by this 2. Because for every 1 A, you have 2X. Be careful with that. It's easy to miss that in a problem. I looked at it and I was like, what? But you need to make sure you take into account the fact that I have 2X to every A. So when I did the practice for the solubility of KaF2, calcium fluoride, I gave you a KSP. Be careful on this. You'll need a 2 with F minus, that meaning the concentration, since there's 2 in the formula. So I solve for KSP, and there's an example just like this in your practice. I said, okay, since I don't know what's going on here, I don't know my concentration of calcium, I don't know my concentration of fluorine, but together, calcium times fluorine is going to give me that KSP value. So 4 times 10 to the negative 8th. What I said was that the concentration of calcium was X. I algebraic. Then my concentration of fluorine is 2X. Good. When I put 2X in here, though, I get 4X squared. So I ended up with 2X equals F. X times 2X squared gave me 4X cubed. And I solved for X. I got 0.0022 molar for calcium and just double that, 0.0044 molar for fluorine. Not too bad. If you look at your practice problems, 49 is easy. It's just writing the expressions. But if you check out 51, I wanted to make a note that when it says molar solubility in part A, it's going to be your value for calcium and twice that for fluorine. Molar solubility is literally that. It goes with one element, and you have to take the 2 into account if there's 2 of that in the formula. So that was just my one clarification. That's really the only new thing to be careful of here is when you're calculating, make sure you multiply your molar solubility by 2 if there's a 2 in the expression. Other than that, it's K Again, made easier by the fact that it's a heterogeneous equilibrium. That's it.